Uh, there's a question about question 38 from Top Hat. And I believe it's because the answer key in the book is incorrect. So let me go over how would you rank these structures, these resonance structures based on stability. And the first rule that I guess we need to, first thing we need rules. So what would be our rules for stability? And number one, the most stable structure is going to be the one with no charges, no formal charges, and all the atoms with a completed octet. And then number two, the second rule would be that we want small charges. So small charges means that plus or minus 1 versus like plus or minus 2, and also a small number of charges. And the small number of charges would be, for instance, that there's just one charge or two charges as opposed to 3 or 4. And then number 3, the third rule is we want the charges, if they have to be charges, to correspond to the atom's electronegativity or electronegativities. Okay, so using those rules then, what I suspect is, I think there's a miss that the answer key is wrong in this case, because if we look at the rule number 1 for what is most stable, and I'm going to use number 1 as most stable, the most stable one would be the C double bond O with the CC double bond, because there's no charges, and all the atoms have completed octets. Now, we are missing a couple lone pairs, but still, the atoms all have completed octets, so I would call that one number 1. I believe they call that one number 2. I'm not quite sure why. So that is, in my book, that's number 1. Then if we look across here at number 2, the second most stable of the structures, I believe they call the first one the second, and again, I'm not quite sure why that is. If we're looking at small charges, in this case, we want the small charges to actually be next to each other, because that's the way that the bonds would actually be polarized. So I would call this one number 2. Why? Because a carbon-oxygen bond is going to be naturally polar covalent, and the oxygen will be more electronegative to than the carbon. So if I had to break up the CO double bond, I would give both the electrons to the oxygen, leave the carbon with none, and so in this case, this would fall. This is basically has charges. It's got small charges, but the charges are next to each other, and the charges actually make sense in terms of the polar covalent nature of a CO bond. If we look at the first one, which I would call number 3, simply there's no real need to, actually I don't know that I would call that number 3. This has the charges next to each other, but why would we, if we had 2 carbons next to each other, why would we actually take the pair of electrons in the double bond and give it to one carbon over another? They have the same electronegativity. So actually, in this case, I could make an argument that this one would be number 3, simply based on the fact that the charges are next to each other. But I could also make a case for it being number 4, because over here, this one on the end has the natural electronegativity in terms of the oxygen being more electronegative, so wanting a negative charge versus a carbon that wouldn't. So I could make a case that this one would be either, number 3 or number 4, depending on well, do we call it number 4 because the negative and positive charges are spaced, away from each other, or do we call it number 3 simply because the negative charge is on the oxygen, which it should be, and the carbon has a less electronegativity and is able to form the positive charge. So this is actually, in my opinion, a poorly worded question, and it's not something that we would do. We'll go over some resonance structures in class that are far more important and will be more along the lines of what we really should be doing. I will just add one thing in terms of the conversion of the far right structure into the one to its left. Anytime you have a negative charge on an oxygen, you have 3 lone pairs on that oxygen. A single bond and 3 lone pairs. A double bond and 2 lone pairs is an oxygen with a 0 formal charge. If I wanted to convert the resonance structure all the way to the right, I would take this pair of electrons, move it here, and then take this pair of electrons and move it there, and that would give me then the resonance structure that has no formal charges. And actually that's how we would form that resonance structure for all of these. We would take this pair. A C with a minus charge always has a lone pair, so we would take that pair to form the double bond. We would take this pair, any of those 3 pairs, and use it to form the CO double bond. So unfortunately 38, in my opinion, is kind of a poorly worded question, but it at least gives me the opportunity to say this is how we're going to rank resonance structures, and these sets of rules are: number 1, if that doesn't break the tie, then number 2. If that doesn't break the tie, we move to number 3. So these are sequential rules that we'll use with all resonance structures to determine which one is more stable and to rank them.